Good morning, ma'am.
Good morning. Just a second. Okay, already participants. Let's wait for a couple of minutes so that at least there are more than 30 students before we start the class. Okay, let us start our lecture 3. So we finished on discussing asymptotic notations and how, if you're given a mathematical function, which you get after calculating the runtime of your program, how do you find out whether your runtime is big O of something or omega or theta of something. Okay, so we'll just go over that big O and asymptotic notations a little bit, and we'll see how we visualize using graphs. Simple, like we did the example last time for mathematically proving that something is O of something or omega of something or theta of something. And then we'll come to the last part of that first lecture where we calculated the run times for for a program. We did for if else, consecutive statements, loops, double nested loops, but we did not do for recursive uh, function calls in a program. So that is basically covered in the topic recursive relations. Okay, here. So after that, we'll see what are the different methods to solve those recursive equations. I'm not able to write on this. Okay, so this is what we saw last time. We are basically comparing functions. So when we say less than or equal to, it is actually, you have to imagine this graph. And in this graph, you have to imagine what grows, which function grows means which one lies higher above in the graph than the other function. So your x-axis is your n and your y-axis is the fn, which is the function that defines your runtime. So the first one is your theta, where fn lies between gn and for two constants c1 and c2. The second one is f1 is less than your cn, and the third one fn is greater than cn. So if fn is greater, you use omega. If fn is less than, you use big O. And if fn is equal to, again not in the actual sense of equal to, then you have this. Okay, then you have theta notation. So a function, like we saw in the mathematical example last time, a function is theta of another function if that function fn is O of gn and it is also omega of g. Okay. So how do we visualize orders of growth? Your x-axis is n, which is the input size. So what we want to see is if our program has to do a lot of work with a lot of input, how will it behave? So the function that defines its runtime, this is how it grows. So if you see, you have two functions here. One is 30n plus 8. So this one defines the runtime for one program. And another is n squared plus 1 that defines the runtime for another function. Select some light color. Okay, so if you see, initially FB in the graph, it lies below FA. But after this point here, not able to draw on this. After this intersection point, you can see here, if you can see my mouse moving, then FB grows faster. So it has higher value than FA. So when you're comparing these two functions, this is what we want to show, beyond which point does your function grow faster than the other function, and that will actually describe the relationship. Okay. So how do you find from a given function, how can you say what is the runtime? If it's a simple polynomial function of degree d, then we straight away say that fn is O of n to the power d, the degree. Whatever lower order terms, we drop them. Like you saw, I gave you the example where the majority of the time that is spent by the function is in, let's say you have a nested loop which has 3 for loops. So obviously a lot of time is going to be spent in that loop rather than a single for loop which lies ahead. So when we talk of efficiency, you improve where it takes most of the time. You cannot improve somewhere which doesn't affect the overall running of the program. I gave you an example last time. So we drop the lower order terms and we just keep the higher order terms and we just write O of that. So if you have a polynomial 3x cube plus 2x, then x cube, you see the highest degree. So it is O of n cube. Okay. So like the example given here, 2n is O of n, and 2n is not O of n square. You don't see the coefficient, you see the exponent. So you see the highest degree. So again, 3n plus 5, it is O of n, it is not O of 3n. This 3 is insignificant when you talk of higher values of n. So again, you have this another property, which I have highlighted here in bold. It says if a function t1n is O of fn and another function t2n is O of gn, okay, then if you add the two functions together, so if you add t1n plus t2n, the overall runtime will be the maximum of the two, okay. And if you multiply the two, t1n, if you multiply the two functions, then the resultant, whatever you get, it will be O of fn into gn. Okay, just like addition, you take the maximum of the two, and multiplication you multiply. Just like in loops, we multiply the two loop variables, and in consecutive ones, we take the maximum of the two. Okay, so for example, you have this example here, 2n plus 10, it is O of n. Remember the rule that you have to take the highest degree of the polynomial. Okay, so that's done. But now if you have to prove, how is it O of n? When is a function O of n? When it is less than or equal to c into n, some constant, and the your gn here is n. So if you see here, in this line, this is what we have to prove. Now you just exchange the variables, you get 2n on the other side. So cn minus 2n is greater than or equal to 10. And if you keep n on the left hand side, you get this equation here. Okay, so n is greater than or equal to 10 divided by c minus 2. Now c is a constant which you have to choose. The constant is not going to be uniform across all functions, across the same function every time. It all depends on what you have to prove. If you are able to prove that something is right, this equation is correct for some value of c, you are done. You don't have to worry that last time I did a c equal to 5 and this time I'm saying c is equal to 10. So in this case, if c is equal to 3, then you get 10 divided by 1. So your n0 is 10. For all the values of n greater than 10 and c equal to 3, this equation is true. So similarly, when you have 7n minus 2, it is again O of n. So again, we'll do the same thing. 7n minus 2 is less than or equal to, here, less than or equal to c into n. Now, when you get n to one side, you'll see that for c equal to 7 and for n0 equal to 1, 7n minus 2. Let's do it on the whiteboard. So you have 7n minus 2. Okay. Okay, somebody wants to do it. You can do it. Please go ahead. Okay, 7n minus 2 is less than or equal to c into n. This is what you want to prove. Your gn is n and your fn is your 7n minus 2 here. Okay, so take n, let's put cn minus 7n is greater than or equal to 2. Okay, so n is greater than or equal to 2 divided by, sorry, c minus 7. For n, if I choose c equal to 7, so I'll get 2 by 0. Okay. So 2 by 0, anything divided by 0 is not defined. So we have to take c greater than 7, not greater than or equal to. So when it's 8, so you get 2 divided by 1. So n is greater than or equal to n is greater than or equal to 2, or you can say n is greater than 1. Okay, so if you see here, just a second. Okay, so you're getting c is equal to 7 or greater than 7 and n 0 equal to 1. Okay, similarly, now we have a higher degree polynomial, 3n cube plus 20n square plus 5. So you have to drop the lower order terms. So 3n cube plus 20n square plus 5. Let's do it here. Three n cube plus 20n square plus 5. This should be less than or equal to c into n cube. Okay. So when will this be, if your c, if your c is equal to 3, so if c is equal to 3, this is never going to be equal because this part is added to 3n cube. Okay, so 3n cube plus something is cannot be less than or equal to 3n cube. So let's say 3n cube plus again 20n square plus 5 is less than equal to 4 into n cube. Okay, so this may or may not be true. It depends on the value. So if n is 1, you get 3 plus 20 plus 5, which is 28, less than or equal to 4. Not true. If n is 2, you get 24 plus 80, which is 104, 109. And that is less than or equal to, again, wrong. If n is 3, let's see, it will be true for, okay. For n equal to 3, 27 into 3 is 71, 8, plus 180 is 250, around 255, something like that roughly. And n is 3, 27 into 4. Again, it won't be right. So if you go on seeing for which value of n this equation is satisfied, you'll see that this will be for n not equal to 21. That is when the right hand side will be greater than the left hand side. So that is when this will be true. Okay, so you see here for n0 equal to 21 and c equal to 4, this equation is true. Then you can say this polynomial 3n cube plus 20n square plus 5 is less than or equal to n cube, in the sense it is O of n cube when c is 4 and n0 is 21. So similarly for the next one, 3 log n plus log n. So log itself, log of a number is a very small value. When you do log of log, obviously it will be smaller. So the bigger factor in this is log n. Out of the two terms, log n is the bigger factor, and we don't take that 3 into consideration. So we'll say roughly it is O of log n. And then for which values of c and n0 will this be true? If it is O of log n, this equation should be less than or equal to c into log n. So we'll see that for c equal to 4 and n0 equal to 2, this equation will hold true. Okay, more examples. You see a polynomial, drop the lower order terms. It is O of n4. Second one, O of n cube. Third one, O of n cube. Any constant you see, let's say 10, it is O of 1. O of 1 means constant is a constant. When you say O of 1, it means constant. It doesn't mean 1 step, 2 step, 3 step. So you know it's a constant. If it's going to be 10 now, when you increase n to 100, it will again be 10. So it will not change. So n does not affect the runtime. As n increases, the runtime stays constant. So that can be anything. So if you remember in the first class, we calculated the cost for simple loop and let's say for a simple statement or consecutive statements. So there are two algorithms that are given in front of you right now. In the first algo, I am initializing the array of size n to 0 step by step. So I'm not writing a for loop from 0 to n minus 1. I'm just doing all of them in steps. So let's say each step has a cost c1. So how many steps do I need to initialize an array of size n to 0? I'll need n steps. So n into cost of one step, which is c1. Now on the other hand, if I do it using a for loop, so what we studied in the first lecture, for loop, the internal statement obviously in the for loop runs for the number of times the maximum size of the loop. What is the size of the loop? It will run from 0 to n minus 1. So again, n steps. And there'll be some additional cost for doing some things in the for loop, the checking part. So what happens in the for loop? Just a second. So what happens in the for loop here? Sorry. This for loop here, you have an initialization I is equal to 0. You have a comparison I is less than n. So first time you enter the loop, you just initialize and you check if I is less than n. You don't increment. Rest of the times when you come back after executing the statement, you first increment I to I plus plus and then you check. So for example, this total work, whatever is done every time you come back to the for loop, it is C2. So how many times will C2 be done? So you are checking the first time you enter when I is equal to 0 and when I is equal to n, which is the exit condition, that time also you are checking. So it is one more than n. So n plus 1 times the cost of the for loop, whatever things we are checking there, plus n times C1. So when you add the two, you get this C1 plus C2 into n plus C2. So now it is like, let's say C1 plus C2 is 10, 10n plus C2. let's say it's 5. So again, it becomes a polynomial and we take the higher order and it becomes O of n. Okay. So similarly, you have now another algorithm where you have a double for loop. So you are initializing at a cost of C1. Then you have a for loop where you do initializing at the first time. Let's say we're just counting the comparison and the increment. Cost is C2. Then cost is C2 again for the next for loop, which does the same thing. And then you have this cost C3. C3 in itself is the cost of assigning as well as adding. So you're doing two things here. You're adding two terms and then you're assigning. So addition and assignment. You're doing two things here. So this statement runs, the statement C3 runs n square times because there are two for loops. How many times is this second for loop? How many times do you visit? You visit that C2 into n plus 1. So the first loop size and the second loop size. And this one you visit C2 into n plus 1 here, and C1 is the cost of the initialization. So you add all of them together, you'll see you'll get a polynomial and the highest degree is n square. So it is O of n square. Okay. So this is what we did in the first class. So, so what you can do is, now the example here is 2n square is O of n cube. Obviously, n square grows at a lower rate than n cube. So if you have to prove 2n square is less than c into n cube. And if you are, when you're equating, if you remove the square here, you get 2 is less than or equal to cn. And for c equal to 1 and n 0 equal to 2, this equation will be true. Okay, so same is true for all of these. You can just go through them once I post this lecture. So 30n plus 8, again, for it is less than or equal to cn. For c equal to 31, this is true, and n0 equal to 8. Okay, you can get that from the equation. I'll just leave it as an existing. So if you see, for this problem, they have drawn the graph for cn equal to 31n and 30n plus 8 and n. So we see at the intersection between the black and the red line, beyond that, your function always stays less than cn, which is 31n. So this equation holds true for n greater than n0, which is equal to 8. So like I said, there is no uniqueness for the values of n0 and c. For the same equation, you can choose different values and prove that your equation is right. Okay. So if you see in the first example, we have chosen n not equal to 5 marked in red, and c is 101. And similarly here, it is n naught is 1 and c is 105. So we have to find some constants with which we can prove that our equation is right. You can better to find the lowest one so that you can safely say it, beyond this it is true. But it doesn't matter. You just have to prove that if you're writing something is O of something, you can prove it on paper using two constants n0 and c, which can vary depending on who solves the problem. So both will be correct. So similarly, we want to say that something is omega of n. So again, omega means if 5n square is omega of n, which means n square grows at a faster rate than n, which means 5n square is greater than or equal to c, some constant c into n. So for values c1 and n0 equal to 1, this will be true. Similarly, if you see the second example, the example is 100n plus 5 is not omega of n square. Obviously, it's not, because we know n does not grow faster than n square. So we have to prove that this is not the case. And for how do you prove? We have to show, we'll prove it otherwise. We'll say 100n plus 5 is less than 100n plus 5n. So, which is equal to 105n. So 105n is actually O of n. Okay, wait a second. Somebody has a question, let me see. You can unmute your mic, Padma. Or you can write your question in the chat. I don't have, okay. Who had a question? You can. I've asked you to unmute, so if you want to unmute, you can unmute and ask your question. You have to press OK. I unmuted your mic. Okay, if you cannot unmute your mic, you can just write the question in the chat box. Okay, write it down. Till then, we'll move ahead here. So, if you see this proof, n cannot be smaller than a constant value. So, this is not true. Okay. N can be omega of 2n greater than n cube is omega of n square, n is omega of log n is omega of 2n, but not n square. So there are some more examples which I think you can go through. I'll just leave that to you. This is the relation between the order of growth sets O, omega, and theta. Theta is like intersection of O and omega, where both are true. It is O as well as omega, the relationship between two functions. Okay. These are the common orders of magnitude for different functions. You can see log n is the lowest. Then you have n. So n is higher than log n. You can try putting powers of two values in all these functions and see that beyond, if you see n equal to 8, I think all of these follow the same order. So log n is less than n is less than n log n, which is less than n square, which is less than n cube, which is less than 2 to the power n. So this is what you should visualize when you see two functions or you see the runtime of a program in terms of a mathematical function. This is how you have to imagine the growth of the function based on the size of the input. So these are common ones you should know. Even if you don't know what is the relationship, you can just use some values. Maybe for some initial values, you don't get any pattern, but as you increase the values, you will see some solid pattern of how they grow, and then you'll be able to safely say if something is O of something else. Okay, this is one table which shows the execution times based on, see how they have changed the values of n from 10, 20, 30, 40, 50 to 100 and even up to 1 lakh, 10 lakh, and so on. So whenever you're given functions for comparison, this is how you can do it if you're not able to prove it otherwise using with the already defined methods. Okay, so this we discussed last time also. We'll be using it again in later slides. You can use, mostly we use binary logarithm in case of many problems that we do, because we have quick sort, merge sort, where we are always dividing by 2. So if the input is of the magnitude of a power of 2, then you can, it's easy to solve those equations. You'll see that in a while. Okay, so what is important here is this one formula. So a log b, x can be written as x log a to the base b. And if you have to change bases, you should use this one. How you change the base of the log. And you know this log x, y is log x plus log y, and log x to the power y is y log x. Okay. So normally you'll see log n written. You don't have to specify the base. Log n, generally it is to the base 2. Otherwise we write ln, natural ln. So log n is log to the base 2n. Otherwise it is ln to the base 10, which we normally use. Sorry. So this one slide I want you to, I'll post it up later in the classroom. So you have to, there are some examples given, you have to uh, write it down. And if you say, let's say log n square is, for example, O of gn. If that is true, then just prove it the way we did a few earlier examples. So go through them again and then see which equation is true out of these. And if it is true, and which one is correct, and if it is correct, you prove how it is correct. If it is incorrect, then you prove how it is incorrect. You can prove the inverse to prove that particular thing is incorrect. Okay, so this I will leave as assignment 1 for you. Okay, I'll mail it, I'll put it on the classroom also in assignment 1. Okay, so again, still discussing asymptotic notations. When you have an equation like this, you can write it in a shorter form where you just keep the higher degree and keep the lower degree as theta of n. So on the left hand side, you see you have 2n square plus now theta of n. And on the right hand side, we are saying it is theta of n square. You can always, like I said, there's no uniqueness of constants of which you can choose. Once you're given the left hand side, right hand side, you can always choose something to make the equation valid. So that depends on you how you proceed. You can choose any constant as long as you're able to prove that what you claim something is O or omega, it is like that beyond that particular point n0. Just a second, give me. Okay, so just a second. Okay. Okay, so before we move ahead, once you do these examples, things will be a little more clear. Then what I want you to go through is some kind of uh, mathematical induction problems, simple ones, so that you get the hang of it. If you don't remember how you used to do proof by induction. So what we do in induction, if you're given a mathematical equation and you have to prove something is true, you first check the base case. Then you have the inductive step where you assume that something is true for n, and then you have to prove it is true for n plus 1. Okay, and then we solve it in such a way that we break it down from n plus 1 to n, so that we can claim uh, that what we had assumed in the initial stages is true. Okay, so for example, if you have to prove that 2n plus 1 is less than or equal to 2 to the power n for all n greater than 3. So if n is greater than 3, your base case is when n is 3. So when n is 3, 7 is less than or equal to 8, which is true. Now your inductive step is we assume this is true for n, and then we have to prove it is true for n plus 1. So you first write down the equation for n, and then you have to prove it for n plus 1. Just substitute n with n plus 1. Then reduce this problem of n plus 1. 2n plus 1 is equal to 2n plus 1 plus 2. Yeah, you multiply this 2 here. This 2 is moved out and this 1 is moved in. So 2n plus 1 plus 2 is 2n plus 1, we know 2n plus 1 is 2 to the power n, right? Plus 2 is 2 to the power n plus 1, which is true. Okay, I'm sure you must have done many problems like that. This is used in one of the methods we use for solving recurrence relations. Okay, now coming to the recurrence relation. So when will you find a recurrence relation in programming is when you write a recursive function, because recursive function is defined in terms of itself. So the definition of a recurrence relation is also, it is an equation which is defined in terms of itself. So when we write a recursive function, you must have seen for many recursive functions that you've already written, like Fibonacci series, you are given a recurrence relation, which you have to implement, and you choose to implement via recursion because it's easier to follow. A less number of steps in the code. Writing is easier as compared to iteration in that case, although debugging, etc. is not easy comparatively. Okay, so you have a term expressed in lower order terms. So you go to solve the lower order problem so that you can find the problem, find the solution for the higher order problem. So obviously, just like we say in recursion, you should have a base case or something which will make you return. So exit from the recursive calls. You keep on calling and there should be somewhere you stop. Otherwise, you'll have stack overflow inside your system where functions keep calling each other without halting anywhere. So again, similarly for recurrence relations, you should have a base case, and whatever calls you are making, you should have to write your program in such a way that it will obviously terminate at the base case. Okay. So simple recurrence relation for Fibonacci number is this. So it's 0, your fib n is 0 if n is 0, if n is 1, it is 1. And if it is greater than 1, it is fib of n minus 1 plus fib of n minus 2. You see the right hand side terms are going down towards your base case, which can be n equal to 1 or n equal to 0. So how do you write the Fibonacci number recursive function? So it's a recursive call. There are two cases. If n is 0, then you return 0. If n is 1, you return 1. Else you return the sum of the two terms, n minus 1 plus n minus 2, which leads to branching of your recursive tree, and you have two function calls now, which will in turn call two more in case they don't terminate at 0 or 1, and so on. So again, something like this is also a recurrence. So if n is 1, your Tn is constant, and if n is greater than 1, this your recurrence says Tn is equal to twice Tn by 2 plus Cn. So here, if you see, we are defining fib n in terms of lower values of n. Again, here you have a function Tn which is defined in lower values of n. N by 2 is lower than n. Okay, so here are some more examples of recursive equations that you'll find. You'll see in many of the algorithms in the initial stages, you'll see we will solve the problem using recursion, and we will first of all make a recurrence relation so that we can define our problem in terms of smaller subproblems, which intuitively are easier to solve because they are of smaller size. Okay, and then there are different ways of handling them. So these are some different examples of, you'll have kind of a base case everywhere. Here you base case is n is 0. Again, in this one, n is 0. Third one, n equal to 1. Fourth one, n equal to 1. Now, if you have written this program here, and I want you to do the runtime analysis of this. So this is a if, there is no else, so you'll just consider whatever is done here. Again, you have a if, no else, you'll consider, let's say it's one step, return is some cost C1. So C1 plus C1, okay? If it is n equal to 0, it will be either of the two, so you can take maximum of the two, okay? In case there are different things going on in the two if conditionals. And then what do you do for this? This calls two similar functions with lower values of n. So if the runtime for, let's say, fib n is t of n, what will be the runtime for fib n minus 1? It will be t of n minus 1. Because our runtime is dependent, we are equating with the input that we are getting. So if you see here, if let's say in the third example here, if you remember your merge sort or quick sort, you were actually dividing the problem into two similar subproblems and then solving those two similar subproblems using the same method. Okay, so you're breaking down your size of input into two inputs of similar size, smaller size, n by 2, and then you're doing some additional work to, let's say, merge them or sort them. Okay, so once you get this equation, let's see if I have, okay, let's do it here. Let's do a, So if you have a recurrence relation, if something okay, so I'm giving you a base case t of 0 when n is 0, t of 0 is 1. And this is my recurrence relation. So I am writing a recursive function where with input n, I'm making a recursive call with input n minus 1. And there is some plus 1 time extra to do something, for example. So mathematically, how do you go about? I know t0 is 1. If I solve it like this, I say t of n minus 1. Now, if my problem reduces to n minus 1, what will you do? Substitute n minus 1 in this equation. So you'll get tn minus 1 is equal to tn minus 2 plus 1. So now I want to know what is t of n minus 2. N minus 2 is t of n minus 3 plus 1. So what is t of n minus 3? N minus 3 is t of n minus 4 plus 1, right? So I'll keep doing it till I reach something like t4 is t3 plus 1. t3 is t2 plus 1. t2 is t1 plus 1. And then t1 is t0 plus 1. Okay. Now I've written down like the expanded form. I know tn will give this, but then tn minus 1 takes this much time, then tn minus 2 takes this much time. So basically, what is the total time taken to solve my problem is the sum of all these runtimes. Because first here, if you see here, okay, this was the time taken to solve the problem with input size n. And this input size n, so basically, in a way, if you pick this up, you can replace it here, right? And then in this tn minus 2, you pick up this equation and replace it here. And so on, you have to do. You replace, and whatever comes on the right hand side, you'll add them. Another way is to simply add all these. So when you add all these, because we are actually calculating all the different time, tn minus 1 will take this much time, n minus 2. So we are adding all of them. When you add all of these equations, you'll see these will cancel out. 2, 2, and 1, 1. So what you are left with are these ones all the way here, 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 and here. And you also have this t0. So how many ones will be there? You are moving from n to 1, tn to 1. So n times 1, this is plus t0. t0 is also 1. So n plus 1. So this is your runtime for this equation. So this is just one way of solving. Obviously, not all equations are such that you can just cross off the left hand side and right hand side. They can get complicated. So that's why we have different methods to solve recurrence relations. Okay. I'll do another example here. If I just change, I change my wait. Tn minus 1 plus n. So again, if you see, if I do it the same way, n minus 1 is t of n minus 2, but this will be n minus 1. T of n minus 2 is t of n minus 3. This is n minus 2. So let's say t of 4 will be t of 3 plus 4. T of 3 be t of 2 plus 3. T of 2 is t of 1 plus 2. T of 1 is t of 0 plus 1. Let's say t of 0 is equal to 0. So this term is just ignored. Again, how do we calculate what is the actual runtime? We'll add all of them. So this and this cancels. This will cancel with the previous term. So what you are left with is this part. What is this? This is sum of all the numbers from 1 to n. So what is the sum of this series? N by 2 into 1 plus n, which is n plus n square by 2. So again, you're getting this in a polynomial form. Highest degree is n square, so it is O of n square. Okay, so this is one easy method of solving. You can call this iteratively. You are expanding the lower order terms and then you are basically, or you are substituting it. So you can either substitute or you can do it iteratively. Okay. Aman, just check who is there.
I'm not from our class.
So how did they join? Enrollment? Okay, let me know the name. I'll just exit.
Ma'am, this Jishan Ahmed.
Okay, just a second. Okay. Is this screen visible, the PDF?
Yes, ma'am.
Ma'am is showing whiteboard.
Still showing whiteboard?
Yes, ma'am.
Yes, ma'am.
It doesn't switch it this way then. Okay. So there are many methods, but the 4 main methods that we discuss are iteration, substitution, recursion tree, and master method. Master method is just, it's like a theorem that is given to you and you have to apply that on the equation. So it has a lot of cases, 2, 3, 4 sometimes. So let's first take the iteration method. So what we did just now was iteration. We'll just show you by example. So we are trying to convert your recurrence into a summation, mathematical summation, so that we can add the time. So if it comes in a proper known geometric progression or an arithmetic progression, then we can just add them using our known formulas that you've done in maths and then get the answer. Answer in terms of a polynomial or logarithm or exponent, whatever it comes to. So we iterate the recursion until the initial condition, which is what we did right now. We went all the way down to T0, which was given to us. And then when we have it in the expanded form, we add them and find the, or sometimes we do a back substitution. So back substitution is, we don't write new terms, we just expand the right hand side. We keep on expanding till we see a pattern And then from that pattern, we derive a mathematical formula for that. So, for example, this is something similar to your merge sort, quick sort. It doesn't have the n factor. So Tn is Tn by 2 plus C. Okay. So just like we expanded n minus 1, we are expanding n minus 2 now in this case. So we get Tn by 4 plus C. N by 4 is n by 8 plus C, so on. So T4 will be T2 plus C. T2 will be T1 plus C. And so since it's a binary type of n equal to n by 2, so your base case will be T2. T2 is equal to T1 plus C. So last May, when you are left with two elements, let's say in merge sort or quick sort, then you get T1, one each in each of the directions, and C. So till here is where your iteration ends. Okay. So now if you add this, the equation such that left and the right hand side will cancel. So what you will be left with will be the plus C term. Now, how many times do you have this plus C? Right? It's not simple. N is not going down like n minus 1, n minus 2, n minus 3. It is going down. It is getting reduced by half. N by 2, n by 4, n by 8. So it is following the same pattern which you have seen in the tree structure that we did for merge sort. So the height of that tree, if you remember, if there are n nodes, the height of the tree is log of n, if n is the total number of nodes. So the height, if I draw the same thing, there's the recursion tree method, that's what it does. If I draw the same thing in a recursive tree, so you have n gets divided into n by 2 and n by 2, n by 4, n by 4, like this. Let's say n is equal to 8. So this will be for, and at every level you'll see there's a C factor. If n is 8, this is 4, this is 2, and 8 by 8, these all will be 1. So this is a binary tree. What is the height of a binary tree? It is log of n, which is to the base 2. Now, how many times log of n? The height of the binary tree means this is the height, in the sense you go 1, 2, 3 steps down. At every step you have this additional work C. So it's actually C into log n. But then again, C is a constant, so we don't worry about that much. So it is actually this C into log n. T1, let's say T1 is 1, so it will not matter. And you see that we say that Tn is O of log n. Okay. So this is what we are actually doing. So either you do it this way and then you add and cancel the left and the right hand terms, or you do it this way. We first see, Tn, this is our base equation, the first one. Then Tn by 2 can be calculated from the base equation. Tn by 4 again can be calculated from base equation. Then we do the substitution. Iteratively, we substitute n by 2 with the C plus n by 4. Then we substitute n by 4 with C plus n by 8. Okay, and the previous C's stay there. So if you see in the next slide, when you do this substitution, what we do is if you see, what is the pattern here? So let me do it on the whiteboard. That's better. C plus n by 2. So you have Tn is equal to C plus Tn by 2. Okay. What is Tn by 2? If you substitute in the original equation, sorry, it is C plus Tn by 4. What is n by 4? It is C plus Tn by 8. Okay. We can go on. If I just write it down like this for now, 3 into C plus T by N by, it's the same thing, right? So if I do it one more time, for example, this will be 4C plus T n by 16, which is n by 2 to the power 4. So I can give it a general form. As I'm iterating, this is the general equation that I'm getting. Okay, so this Tn is basically equal to this general form. Okay, so it will be k times C plus Tn by 2 to the power k. What is the base case? Our base case is T1, right? So our base case is T1. When will we get T1 from this? When n is equal to 2 to the power k. When when n is 2 to the power k, we are actually iterating. So n by 2, n by 4, n by 8. We want to get 1. We'll get 1 when n is equal to 2k, which is, if you apply log on both sides, log n is k log 2, or k is log n to the base 2. Okay, this is the substitution. When we do this, we get T1 here. And we have k into c. T1, let's say T1 is 1, some 1 unit of time. What is k into c? Your k is log n to the base 2 into c. So this is basically our answer. This is what we got doing it this same way before. Okay. So we see the pattern in the equation by doing multiple resubstituting or iterating on the right hand side, get a general form of the equation. Sometimes it might not be simply like this is k times c. It can be some kind of a summation also here. That's what you have to look for. And then you can find the answer. We'll see more examples here. So k times c into log n, because n is equal to 2k, and this becomes over theta of log n. Sorry. Now this is a similar example with the difference that you have n instead of c. Okay, so when you have n instead of c, okay, let me do it on the whiteboard. It'll be easier to understand. Tn is n plus Tn by 2. So keeping the left hand side same. When you substitute n is there, now you have to substitute Tn by 2 with n by 4. Sorry, to find Tn by 2, you substitute Tn by 2 here, you get n by 2 plus Tn by 4. Right? Then you have to find what is Tn by 4. Tn by these two terms stay there. Tn by 4 is n by 4 plus Tn by 8. Again, let's do one more. N plus n by 2 plus n by 4. What is Tn by 8? It is n by 8 plus Tn by 16. Now let me write it like this. N plus n by 2 to the power 1, n by 2 to the power 2, n by 2 to the power 3 plus Tn by 2 to the power 4. So how do I write the general equation? I'll take n common. So I get 1 plus 1 by 2 plus 1 by 4 plus 1 by, it is 8. So I just leave the power for a while here. Plus t n by 2 to the power 4. I'll put k for 4, and then this is k minus 1. So this is my general equation. Again, here, if you see on the left hand side, this is a mathematical summation, but I still have to see, this should be reduced to 1. I have to get to the base case. So base case is when n is equal to 2k, which means k is equal to log n to the base 2. Okay, so this, when n is equal to 2k, this becomes t of 1. Okay, so t of 1 is just, let's say, one step. We can just ignore. It's not a polynomial or an exponential value, so you can just ignore. So we have to focus on this. So this becomes n into sum of 1 by 2 to the power, say, I goes from 0 to k minus 1. K minus 1 is plus t1. So what is the, this is a, your A is 1. You should remember the geometric progression. So R is the 1 by 4 by 1 by 2 is 1 by 2. A R to the power k minus 1. See, I just always get confused with this formula. Okay, we did a different example. Okay, that's fine. I think we did not do the example that was given here. Okay, it was 2n by 2. How many number of terms? There are k number of terms, right? So it is, A is 1. It is 1 by 2 to the power k minus 1 by 2 minus 1, which is, I need to erase on this side. Erase this. There was 2n by 2 in the problem that was in the PDF, but anyways, doesn't matter. So I can write it like this, divided by 1 by 2. I just took the minus out the other way around. It's 1 minus, sorry, no, it is 1 minus 1 by 2 to the power k into 2. So it is 2 minus 2. So what is 2k? Your 2k is n. So 2 minus 2 by n is 2n minus 2 by n. I think there's something wrong somewhere. One by 2. Okay, just remember this for now. We'll come to this in a while. I think I have this. So the one example here, so it is, this one is n log n, I guess. I did something wrong somewhere. So I'll do it again on paper and send you a picture. I just don't want to spend more time on it. So this one here is twice n by 2. So if you see here, When you have twice n by 2, this denominator factor that we are getting in the other one gets cancelled. I'll do it again on paper and send you, because I think I did something wrong somewhere. So this is twice n by 2 plus twice n by 4. So this 2 and 2 will get cancelled. So you'll just get n there and 4 tn by 4, and that will be the case. So you'll get k times n plus, you have this 8 here and you have this 8 here. So you get 2 to the power k and 2 to the power k. And when you substitute n equal to 2k, you get kn plus n. So k is log n plus n. So it is n plus n log n. If you remember the graph, n log n is greater than n. So your final answer is n log n. Okay, so this is, can you see the PDF? Aman, can you see the PDF?
No, ma'am, it's showing the whiteboard.
Acha. Okay, I was explaining on the PDF. I forgot to switch. It says you are screen sharing, so then I don't know, it doesn't switch over. Okay, so I was actually telling you the actual problem that was there. That one I will do again on paper, because I think something wrong I did somewhere. This one has twice tn by 2, so your 2 in the denominator, 2n by 2, it will cancel to n. So you'll get n plus 4 tn by 2 here. And then when you expand, you get k times n plus 2 to the power k tn by 2 to the power k. And when you do the substitution, n is equal to 2k here. And then you get kn plus 2 to the power k. Okay, k is log n log n plus n. From the graph, n and n log n is greater, so you get that. So this is another recurrence. This is a simple one, kind of similar to the one we did in the beginning. Tn is tn minus 1 plus c. So they're not doing the way we did it by expanding the equations. They're expanding it on the right hand side. So you see Sn minus 1 is c plus Sn minus 2. Sn minus 2 is c plus Sn minus 3. So you get k times c in the end and plus Sn minus k. And when will you get S1 or S0 is the base case? If you see here, you have S0. So when n is 0, when will n be 0? When n is equal to k. When n is equal to k, then you get this equation and you get the answer as Cn. So in general, Sn is equal to Cn. This is the same problem we did in the beginning on the whiteboard. Just says Sn, that was Tn. So again, we did this also on the blackboard. This is the one. This is Tn is equal to Tn minus 1 plus n. So we got this series n up to 1. You see here. So you got summation I plus Sn minus k. When n is greater than or equal to k, we have this. And k is equal to n, which is our base case. We get summation n into n by plus 1 by 2, which we got as n square plus 1 by 2, which is O of n square. Okay. This is again similar problem. We have twice tn by 2 plus c. Since you have this 2 factor here, you'll get simply the summation of these c constants. So again, see here they have iterated down to this level, 2 to the power 4. Then they replace it with 2 to the power k. And when n is greater than 2 to the power k, then your equation, it obviously you need some more iterations to go. When n is equal to, it's actually 2 to the power k here. When n is equal to 2 to the power k, k is log n. Then they are replacing k with log n. and you get 2n minus 1 plus into C. Okay, just it's better to write it down and solve it so that you get an idea what is happening, and you can refer to this slide. Again, the recurrence that you see here, it is a general recurrence. Tn is a into t n by b. A and b can be anything. So here they are solving a general one. So a can be 2, a can be 1, b can be 2, b can be 3, and so on. And you have Cn here. This is a function. Okay. This is Tn is equal to a into t n by b plus something, plus some function c into n. So again, you have to do the same thing. Keep on iterating by substituting, in this case, let's say a into tn by b is substituted with a into tn by b, obviously. When you replace n by b, so it will be n by b square plus cn by b, and then this is the previous cn. So when you expand it, you get a square, okay, like this. Change the color. So on. So then they get this. This is the, after you iterate, they've just clubbed all the terms together. This is what you get. And to generalize it, if you put it in terms of k, this is what you get. Ak tn to the n by b to the power k plus, this is, if this is k, this is k minus 1 here. So you get this equation. Okay, so this equation, there is one t term, so that will be 1 t equal to t1 here, this part. This part here, this has to be reduced to, you have to reach to the base case when n is equal to b to the power k. So that is here. Okay, so when you substitute that, you get this here, and you still have this summation. If you see, the summation ends at a to the power k minus 1. They have modified this first term here because they want to generalize it. It is in terms of a and b. C a to the power k. They have n is equal to bk, right? Here. N is equal to bk. So if you see this equation, it is nothing but c into ak because n is equal to bk. But using this, they have been able to move this inside the bracket, and you get the series, the geometric progression where the r value is a by b, and it is from 1 to k. If you see in the next slide, now you have a series simply. Cn into the sum of the series. What is the sum of the series? It is, let's do it on. Okay, so before they are going ahead, this is our general equation, you keep in mind. Now, if your A is equal to B, for example, you have Tn is equal to twice Tn by 2 plus Cn. So A and B is same. So if you see this equation, the bracket part is reduced to, k plus 1 terms, starting from k equal to 0. And your k is log n, you get this answer here. Okay. If your A is less than B, then we have to apply the sum of the series x k plus 1 minus 1 by x minus 1. Okay. So this is the series, this is the sum, k plus 1 minus 1 by this, and you get 1 divided by 1 minus a by b, roughly. This is a rough equating at the end of this formula. Please close the door. Okay. So 1 minus a by b, it is kind of changed into a constant value. In the sense, these are constants. 1 divided by, let's say, a is less than b. So 1 minus 1 by 4 will be 0.75, and 1 divided by 0.75 will be a constant. So it is essentially a constant value because a and b are numbers. There is no n associated with them. And if a is greater than b, then you cannot do what we did in the previous one. You cannot equate it to this 1 divided by 1 minus a by b. You have to have it, the formula as such, and we take the highest term in this, which is a by b to the power k. What is a by b to the power k? It is actually a to the power k divided by b to the power k. What is k? K is log n to the base b. So if you see the substitution that is here, a to the power log n and b to the power log n. So if you remember the formula, a to the power log n is n to the power log a. B log n is n. So a to the power log n is n to the power log a. So I'll just come down here. So if you have a general equation of the form Tn is equal to a t to the Tn by b plus Cn, then there are three cases that arise. If a is equal to b, you have n log n. If you remember, a is equal to b in case of quicksort and in case of merge sort. That's why for both the cases we get the runtime n log n. Okay. And for the rest, if a is less than b, it is theta of n, and if a is greater than b, it is theta of n to the power log a to the base b. Okay, you'll see a lot more of this in the master's there. Now you see most of the times you either use big O or you use theta. If you are using theta, it automatically means it is big O also. And it is omega also for some constants. Okay, so safer is always to use big O and theta. We generally, like I said, we don't use omega because that is greater than. It is theta. Theta would mean it is in a range of values. So it is, when we say equal to, we use theta, or you can use omega. There's no, at this level, that's okay to use both of them. Okay. So this was your iteration method. Next is your substitution method. Substitution is, you see a recurrence relation, you guess the solution should be, let's say, log n, or it should be n square, and then you prove by induction. How do you guess that the solution is n square or log n? You put some values of n and see the pattern, and like mathematicians say, oh, it's following an exponential pattern, it's following a quadratic pattern, but then you have to justify or prove it. So you will prove it using mathematical induction. So for example, if we guess that for a particular recurrence relation, it is O of Gn, that means it is less than or equal to Gn, some constant into Gn, then we have to prove it using induction. So again, to create the induction hypothesis, you have to know what this D is and what this N0 is going to be. Okay, that will make your induction strong. So for example, you have this equation. Tn is twice Tn minus 1 plus 1. So what we do is, base case is T0 is 0. So what we do is we calculate, we make a table of some basic initial values. So if you see the answers as in the Tn values, this box is Tn here. If you see 1, 3, 7, 15, 31, 63, 127, these are all very close to powers of 2, 1 less than in all the cases. So we assume that Tn is 2 to the power n minus 1. Now we have to prove. We see that pattern, but you don't know whether moving ahead after 7, that pattern will be followed or not. So we have to prove by induction. So our base case is when n is equal to 0. So 2 to the power 0 is 1. So base case is true. Now we assume that Tn is true. If Tn is true, then Tn is equal to 2n minus 1. Okay. Then we have to prove Tn minus Tn plus 1 is true. Okay. So your Tn is 2Tn minus 1 plus 1. So when you substitute, you get 2n minus 1, right? That's fine. Wait. So we are proving they have done it the other way around. They have used n minus 1. They have substituted 2 to the power n minus 1 in case of Tn minus 1, and they get 2n minus 1. So it is the same. Okay. Another example, you have the recursive equation. This is the one we just solved. Tn is Tn minus 1 plus n. They're guessing it is n squared. This is the one in which we got n by 2 into 1 plus n. And Tn is less than or equal to c into n squared. So Tn is Tn minus 1 plus n. So if we are saying it is n squared, it should be less than c into n minus 1 whole square plus n. You expand this and you see it can be written in the form, this form. So you are subtracting something from cn square. So obviously it's going to be less than, but provided this value inside the bracket here, this is positive. If this value is positive, then this equation is true. When will this be positive? If you put it like this, it is positive when c is greater than this value here, and then you can find out what c value will work. C is greater than 1 by 2 minus 1 by n. So if n is 1, c is 1, and that will work for this example. Okay. Again, similar problem that we just now did. We are assuming it is n log n, which it is, and you have to prove that Tn is equal to twice Tn by 2 if it is less than this. So left hand side you substitute Cn log n minus Cn plus n. Okay. What if you see this equation here, if you can see my arrow, 2Cn by 2 log n by 2. Okay. 2 and 2 will cancel, so you have Cn log n by 2 is log n minus log 2. Log 2 to the base 2 is 1. So you'll just have log n minus Cn plus n. So Cn log n minus n into C minus 1. So provided this here is positive, you are you can safely write this is less than Cn log n. And it will be positive when C is greater than or equal to 1. Again, another example, I would suggest all of you to write this down on paper. You can just use write the first equation and prove it by induction yourself to see. We want to get this Cn log n term on one separately, and we get the rest of the terms separately, and then we can judge or justify how this is true. So another example, just you can just go through it yourself. I don't want to go. I just want to tell you about this one. Sometimes you'll see a equation like here. What you see, it's just a little unknown. I wanted to highlight this part. So you don't have n by 2, you don't have n minus 1, you don't have n by 4, n by 3. You have square root of n. So you won't be able to solve in powers of n. So what we do is we change the variables. Okay. So we rename in a sense. So we say if log n is m, then what is n? N is 2 to the power m. The same substitution we were making earlier, n is equal to 2 to the power k. We're doing the other way around. So your root of n will become 2m by 2 based on this renaming. Now, again, we do a rename because 2 to the power m by 2 summation in powers of 2 will be difficult. So we say let Sm is equal to t to the power 2m. If Sm is equal to t to the power 2m, what will be t to the power 2m by 2? It will be Sm by 2. And we land up with this equation here. We land up with this equation. And if you see, this is the same equation for quick sort, merge sort, and the one we just did. And the runtime will be m log m because we are talking in terms of m right now. Okay. Now m is not our actual variable. Our actual variable is n. How is m and n related? We have that here, right? N is equal to 2 to the power m. So you do a reverse substitution. Replace m by log n and log of m by log n. So this is the runtime. So whenever you see a recurrence which does not seem similar or looks a bit daunting to you, try to get it into, you have to substitute and get it to a version that you're familiar of, that you can easily solve, and then you, in the end, you have to do reverse substitution to get it, get the answer in the actual variable. Okay, so I'll just stop here. I want to go back to that problem which kind of did not end on a good note. Okay, we did tn by 2 plus n. Tn by 2 plus n. Just want to do it again. Let's finish this and then we can end the class. N by 4 plus n by 2 plus n. Tn by 8 plus n by 4. This we did earlier as well. So it is t of n 2 to the power k plus just 1 plus 1 by 2 plus 1 by 4, 2 to the power 2, 1 by k minus 1. So if n is equal to 2k, what we are worried about is the sum of this series. There are, this is 2 to the power 1 and this is 2 to the power 0. So there are k terms. So 0 to k minus 1 is, there are 3 terms, sorry, k terms here. So k terms means, I think it goes like this. I always mess up this formula. I just want to make sure we just came across this. So yes, just k plus 1. No, we just have k terms. We don't have k plus 1 terms. Yeah, we have just k terms. So 1, okay. So we have k terms. So it is 1 by 2 to the power k minus 1 whole thing. Let me write it here on the left hand side so that it fits in. So 1 k minus 1 divided by 1 by 2 minus 1, which is 1 minus 2 to the power k by 2 to the power k. You have minus 1 by 2 is 2 by 1. So 2 minus, just keep it like that. So basically, what is your n is equal to 2k, so you can just write 1 minus n by n into 2. Minus 2 by n. I don't know. This looks very... Missed the minus sign. Okay. Where did I miss it? Okay, minus 1 by 2. So it's n minus 1 by n. Okay, this way. So it is minus into minus 2. So it is basically 2n minus 1 by n, which again looks weird to me, but I don't know. I arrived at the same thing. I'll just check it again. It should be O of, because n comes in the denominator. Should not come in the denominator. Okay, I'll check it again, but up till this point it is correct. I think the only thing maybe n by 2 plus n. I'll check it again. So once you get to something like this, you can because it's n in the denominator, that's why I find it a little weird. So this is your so you whenever you're asked to solve a problem in an exam, solve it in any method, and otherwise unless it is explicitly mentioned. Try avoid using Master's theorem, because that is just like you remember the theorem and you apply it. There's no solving in between. Okay, so let me go back to this. Okay, so we finished till substitution, and we are left with recursion tree and master theorem. So let's do the next two in the next class. If you have any questions, you can just type in the chat box so that I can answer. Who's calling? Okay, you can type your question. I'll just attend this call from office. Yes, any questions? So I don't like to do maths like this. There's a lot more I wanted to do, but it's not, the whiteboard is okay, but not for longer problems. So that slide in which the examples are mentioned, you can do those first. Then I'll give you, or maybe you can just do them on rough. I'll add a few questions on iteration, substitution, and recursion master theorem once we are done as your first assignment for some practice as well. Okay. So any questions? Aman, can you please take the attendance?
Yes, ma'am, I have taken the attendance. I
Take-
mailed you.
Okay,
Okay.
already. Okay, let's see. You have class tomorrow also, but maybe Ruhi ma'am might take my class. In any case, I'll inform you. Okay, so we might change the classes to 3 times a week rather than 4 times a week. Okay, but in
Okay,
that
ma'am.
the new timetable might come by tomorrow. So
Yes,
the
ma'am.
because ma'am wanted a break in between the 4 continuous classes, so we'll take longer classes, but 3 days only.
Yes.
Okay, so you'll get
Yes.
a new timetable for that. All right, thank you.
Thank you,
Thank
ma'am.
you, ma'am.
Thank you.
Thank you.